Now start about reflexive. When a space be reflexive. Okay. Reflexive space. When let X be a normed space. Let X be a normed space. Then X is said to be. Then X is said to be reflexive if the canonical embedding mapping is onto. Okay. Now if phi be bijective, if phi be bijective and X is reflexive, then phi is isometrically isomorphism. Now what do we write? We write X equivalent to second dual of X. Okay. If phi is bijective and X is reflexive, then phi is isometrically isomorphism. Now we write one theorem. Let X be reflexive. Let X be reflexive. Normed space, then X be Banach. X be reflexive normed space, then X be Banach space. That means reflexive normed space implies Banach space. If phi x to x double star or second dual of X is canonical mapping, this one phi x to second dual of X be canonical mapping since X is reflexive, since X be reflexive, then X equivalent to X double star and X double star or dual or second dual of X be Banach, then X be Banach. Okay. phi x to x double star be canonical mappings in x be reflexive, then x equivalent to x double star or second dual of x double star be Banach space, then x be Banach space. Okay, now we're going to further. LP is a reflexive Banach space. Obviously capital LP or reflexive Banach space. Rn and Cn is reflexive Banach space. That means Rn, Cn, capital LP, small lp, all are reflexive Banach space. This one. Okay, 1 less than p less than infinity. Now we're going to further. Then what is reflexive? Just we write this definition: X norm space X be reflexive if the canonical mapping phi X to second dual of X be onto. If phi be bijective, then and X is bijective means X be reflexive. If X be reflexive, then phi is isometrically. That means here reflexive and phi injective, then phi is isometrically isomorphism. Then next, let X be reflexive normed space, then X be Banach space. Okay, now we prove another theorem about this. Here's this portion now. Let X be Hilbert space. And x, y belongs to X with norm of X less than equal to 1, norm of Y less than equal to 1. Then norm of X plus Y whole square plus norm of X minus Y whole square equal to 2 of norm of X square norm of Y square by parallelogram law. Now let epsilon greater than 0 be given that norm of X difference Y greater than equal to epsilon. Then norm of X difference Y square greater than equal to epsilon square. This implies norm of X minus Y whole norm square less than minus of epsilon square. So norm of X plus Y whole square less than equal to 4 difference X minus Y whole square less than equal to 4 difference epsilon square. So norm of X plus Y by 2 whole square less than equal to 1 minus epsilon by 2 whole square. This implies x plus y by 2 less than equal to square root of this one equal to epsilon or delta equal to delta. Hence, what conclusion done? Hence, every Hilbert space is uniformly convex Banach space. Hence, every Hilbert space is uniformly Hence, every Hilbert space is uniformly convex Banach space. And every uniformly convex Banach space is reflexive also. Okay. Every uniformly convex Banach space be reflexive. Okay. Now we also discuss today we also discuss reflexive space. Now we also discuss some properties of orthonormal set. Okay. So we erase that portion. Just let E be an orthonormal set. Let E be an orthonormal set. Orthonormal set in an inner product space X. In an inner product space X, then E is linearly independent. Then E is linearly independent. Okay. Now we write proof of this proposition. Let E1, E2, En be a subset of E. Then Ei is equal to 1 if I equal to j and 0 if I not equal to j. Let alpha 1 e1 alpha 2 e2 dot alpha n en equal to 0 for some alpha I belongs to k. Hence alpha 1 e1 alpha 2 e2 dot alpha n en ei equal to 0 implies that here alpha I ei equal to 0. Another one are remaining ei is equal to 0. This implies alpha I equal to 0 since ei is equal to 1. So for all I, alpha I equal to 0. Then what we get? We get this one. That means we erase our portion. And what we get with that, this conclusion part, alpha I ei summation equal to 0 implies that alpha I equal to 0 for all I. Then E equal to ei, I belongs to this. Oh no, sorry. 1 less than I less than n, B linearly independent. Okay. Now we erase this portion and going to further discussion of Bessel inequality. Bessel's inequality. Let E equal to E alpha. Alpha belongs to this capital phi or index set. Be a countable orthonormal set in an inner product space X. Then summation X E alphas inner product of X norm of mod of X E alphas mod of inner product of X E alpha square summation alpha belongs to index set equal to less than equal to norm of X square. Okay, for all X belongs to X. This one is the Bessel inequality. We have to prove that. What we proceed? We first start this proof. Let X belongs to X and let E1, E2, E3, En subset of E. Then set Y equal to I equal to 1 to N X EI inner product EI equal to summation I equal to 1 to N alpha I EI, where alpha I equal to X EI. Now note that norm of X difference Y square equal to X difference Y. Now this one equal to X difference alpha I EI equal to 1 to N X difference alpha I EI equal to 1 to N equal to X summation I equal to 1 to N alpha I EI X summation I equal to 1 to N alpha I conjugate X EI plus summation I equal to 1 to N alpha I conjugate EI. Next we proceed further. Then what we get? We get norm of x square difference alpha equal to put here x ei, then this one I equal to 1 to n x ei and x ei conjugate. Okay, this eix equal to this conjugate. Next I equal to 1 to n x ei, this one equal to x ei conjugate, this one equal to summation I equal to 1 to n norm of alpha I square. Okay, then next what we get? We erase our portion. Then what we get? We get so simply equal to norm of x square difference. Okay, difference this one here and here, this one equal to x ei norm square I equal to 1 to n. Here obviously I equal to 1 to n x ei norm square plus I equal to 1 to n x ei square. Then norm of x square difference I equal to 1 to n norm of mod of x inner product of x ei mod square. Then what we get? We get norm of x difference y square greater than equal to 0 implies that norm of x square greater than equal to y equal to 1 to n mod of x inner product of this square. So what we conclude? We erase this portion. Since e1, e2, en are arbitrary subset of E, since e1, e2, en be arbitrary subsets of E, then we conclude that this one, this I, this alpha square less than equal to normal. Okay, so we prove this Bessel inequality. If E alpha be a countable orthonormal sets in an inner product space, then inner product of x E alpha norm mod square summation of this less than equal to norm of x square. Okay, now we're going to another definition of Schauder basis. Okay, definition of another basis we known about its Schauder basis. So erase this portion now. We write this definition of Schauder basis. Let X be a norm space let X be a norm space and En be a sequence in X and En be a sequence in X, then En is said to be then En is said to be Schauder Basis if for each x belongs to X, there exists unique sequence alpha n in K. There exists unique sequence alpha n in K such that norm of X difference I equal to 1 to n alpha I tends to 0 as n tending to infinity. That is I equal to 1 to n alpha I tends to X as n tending to infinity. Okay, X be a norm space and En be a sequence in X, then En is said to be Schauder basis if for each X belongs to X, there exists unique sequence alpha n in K such that norm of X difference I equal to 1 to n alpha I norm of this difference tends to 0 as n tending to infinity. That is I equal to 1 to n alpha I tends to X as n tending to infinity. Okay, now Reed-Fisher theorem. We discuss about that theorem. We now erase this portion and going to further discussion about that theorem. Let En be an orthonormal sequence in a Hilbert space. Let En be an orthonormal sequence in an Hilbert space. X and alpha n be a sequence in K. And alpha n be a sequence in K, then the following are equivalent. Then the following are equivalent. First, alpha I equal to 1 to n or 1 to infinity is convergent in X. and number 2, norm of alpha I square is convergent. Okay, then then we just write this theorem, Ritz-Fisher theorem. Okay, we now prove of this theorem, but today we stop here.